Talk's going to be on, he has it kind of misrepresented on the schedule. He said Introduction to S-100 Systems. I was basically, when he asked me to do it because of a cancellation, I'm talking about specifically about front panel S-100 systems. So, you know, M-size Altairs, Ithaca Inter-Systems, DPS-1s, and also there was a Byte 8 had a front panel. Those are the only S-100 front panel systems that I know of. I'm going to kind of talk about just, you know, like why the reason for a front panel, and also some of the basic hardware testing you can do just with the front panel and very limited memory. For instance, if I get a board in, I can test it out. You know, does it work? Just writing some small programs. So that's where we are. I just got to get a few more things connected, and we'll be all set. Okay, unfortunately, I think I might have missed an adapter in my packet, but we can still work around it.
Where's room 1? That's room 1. That's room 1? Okay, no, oh, sorry. Room 2. Yeah, that's okay. Thank you.
So in your experience, are live demos with a whole bunch of card slot things more or less likely to be successful on the first try?
I don't know. We'll find out. Like I said, I kind of got pressed in the servers earlier in the week.
Yeah, because Steve to make an announcement that I've changed, but it's not out already.
Yeah.
Sorry, Raspberry Pi fans.
Yeah.
Right.
But so what happened was, you know, because of that, and then to complicate matters, I lost power on Wednesday. So a lot of this stuff I couldn't test. I was either doing it by battery light or, you know, so, but
exciting.
But I did find out I must have misplaced an adapter, so, but we can still work around it. So, let's see what we got here. Okay, this is just a little terminal, ASCII terminal on a board run by PIC32. So it's just kind of a replacement for a big terminal. You know, that's the only reason I had that little board to just act as a terminal. Let me grab a chair. So this is my test setup. I'll just throw it in. Okay, one last check to make sure I can use that adapter somewhere. Okay. Anyway, we can still work on that. So, this is your basic, you know, this is my test bed. Basically, this is a replacement for an M-side front panel. A fellow named Don Caprio decided to take the M-side front panel, which is like 17 inches wide, shrink it down so it fits similar into like an S-100 form factor. You know, it'll fit the case with every other board. So one of the first things we do, right, we want to make sure, one thing that works nicely on this is if you hit reset, it actually has a lamp test. So, first thing we do, except for these are the like call and run and everything, so that does not become effective here. But all the other, when you hit reset, everything else gets So you say, okay, it's a lamp test, all my LEDs are working. I'm kind of gearing this, it's like you get this stuff for the first time and you want to kind of see, is it working? Just like the old days when we had very little memory, the only memory board I have right here now is a 4K memory board. So, first thing I do when I get a memory board, I mean, you can pop it in a machine, with a monitor and run a memory test, but a lot of times I just like to pop it in. Can I deposit and read from memory? So typically what I do, this is starting at address 0. So if you hit reset, which I did before, okay, so now this is just random stuff that's in memory. So what I typically like to do is just as a test, on a front panel machine, if you want to look at a location set by the address switches, in fact, in this case they're all zeros, you hit examine. And that is what is in memory. So now if you want to deposit, what I typically do is just to keep track of things, I'll deposit like 0 in location 0, 1 in location 1, just go up and say, hey, does it work? So what we'll do is, so now I deposited that in the first location. Okay, there's our deposit. So now I'm going to put 1 in the next location. So if you flip the switch down on most front panels, like the IMSI or the out there, deposit next. Okay. So I just go through like a little binary progression there, just to see, and I'll do this for several locations in the memory board at both ends. This is a 4K board, so the highest address you have is Fox, in hexadecimal. So for instance, if I try to write, if I go to Fox, examine, okay, so right now there's nothing in there, but if I click deposit, it'll put Fox in there. Or actually, let me do a different example. Let me just put 0 Fox. So put 0 Fox in there. Now that's the last memory location in the board. So if I try and now write to one address higher, 1000, show you what happens. It's not going to work because there's no memory there. But the result will give you a clue a lot of times. They're all high, because if you don't have a memory board in there, all the lines, data lines, they tend to float high. So a lot of times, like I've had it where you got to set the address by switches in a board. And what happens is the switch is flaky, and you think, okay, that's at that. You go to write to it, and it's like, why isn't there memory there when there should be? So that's one test I use. Okay, this is the upper. I can write both ends of the board, somewhere in the middle. So basically, not saying the board is perfect. You could still have errors, but at least it's not a paperweight. So that's one thing I did. Now another thing I do usually just to test out the machine, like test out a CPU board. This is a Byte 8 CPU board, by the way, which is one of the front panel machines. I just write just a small little program. All it is it outputs to the these switches over here are what they call programmed input. So you can read these switches and do it for your program. So on most front panels machines, S-100 machines have those. So what you do is, in 8080 code, a dog baker is an input. Okay, the port is Fox. And then what I'm going to do is I'm going to write it, which is a dog 3. These are just right out of the opcode manual, basically. And then I'm going to output it. The LEDs over here are what they call programmed output port. So I'm going to write to that because it'll show up what's on the switches. So I'm going to output. That's also Fox. That's an output ports and input ports can have the same address because the way the 8080 is set up, it has an output and an input instruction, so it knows the difference. And then what we're going to do is we're going to do a jump, which is a Charlie C trig. And then we're going to go, since I started at 0, 0, 0, 0, I'm going to do a jump to 0, 0, 0, 0. And so this is just a real quick program to test out, just to see is, does the CPU, other than the deposit and everything, does the CPU really work? So we're going to reset it. We're back at 0. So the first instruction, fill baker, deposit. Now we're going to be reading these switches, which are Fox, FF, and hexadecimal. Okay, then we're going to be this is the dog 3 D3 instruction. Then we're going to do a Charlie tree. Zero, zero, and then the next one is also 0, 0. We're starting at location 0, 0. Just like as Doug mentioned with the 6502, the low order byte, they're reversed from the way you normally think of the address. In other words, like if I was going to be writing to 8000, the address would be 0080. So in this case, they're both 0, so it doesn't matter. So now if I reset it, there's my instruction. So now if I say run, the interesting thing is, with the way the front panel, inside the front, design the front panel is, it's the complement, it's the inverse of what the input is. The reason they did that, I think they could have used inverters, but I think the reason they did that was to save chips. Because the 8212 latch that's on the board that drives these, it can't source that much current, but it can sink it. So maybe you can get a couple milliamps out of sourcing it. You can get much more out of it sinking it. So that's why they decided to do it in reverse. So what I typically do is, just for the heck of it, right before I'm going to output it, where that D3 is, I'm going to insert a complement instruction, which is a 2F. So that just takes all the bits and complement. So basically, you're right here. I'm going to put 2F. So that, well, you'll be able to read the status as the switches are. And but sometimes it does get confusing because you say, well, it's in reverse. So anyway, so we're going to go down. We're going to examine next. Show you how to modify a program at least. So there's that's my first one. Now here's where the dog 3 is. So here I'm going to put deposit. So now I have to continue on. So now I got to do my my 2 foxes above the dog 3. Excuse me. So now what I got to do is I got to do my D3. See, so now they're true, at least when you turn the switch on. It's a minor thing, but sometimes when you get involved in stuff, I was getting in my mind to put a complement instruction in there because it's like, why is this backwards? I run into it a few times, even running basic programs, because the output ports are addressable from basic. So that's one little step there, just to see, just to give a test on, how this stuff works. Now, you can also test like I/O boards. I was going to test a serial board here. This is a serial port, but unfortunately, I think that's the adapter I'm missing. But anyway, we'll figure something out. So anyway, we'll do a parallel port. So this is a handy little device. This is a logic probe, and you don't need an expensive test equipment necessarily to test things. So this will measure 5-volt levels, and it'll give you a high or low tone. It's audible. So for instance, if I want to test this parallel port here, Okay, so now if you were to check different locations, you get a high or low. That's pulsing. So what I typically do is a lot of times just using the front panel. So this output port is addressed as Fox Charlie. So now it is in a low state. So for instance, if I go into the same test program, I say, I'm going to be reading from the switches. I'm going to, I don't have to complement it. I can actually put zeros in here, which is a no-op for an 8080. Here's my output. Now this port is going to be FC. This is the high order bit on that port. So just by using a logic probe and a small little loop, I can say, well, the port works. You know, you can just go down, I just tack the wire in there, but you can just go down with the logic probe to each port. You can say, hey, this thing works. I mean, this was important way back in the day, because when these things came out, stop that, it's a little annoying. When these things first came out, they didn't have much hardware. I mean, like the basic Altair came with 256 bytes of memory. So the only thing you could do, you can only use the front panel. People do some very creative things with the front panel. You know, you know, one of the early games is something called Kill the Bit, in which it scanned back and forth, and you had to throw the switch at the exact instant that LED was lit. So that was one of the early things that they did. You know, but it was all about learning programming. You know, unfortunately, I'm not much of a programmer, so. You know, my background's in hardware. I like building things. I built an MSI 8080 back in the day, like 77. Of course, I sold it along the way, but this is basically the equivalent on my piece of plywood here. So, but people, like I said, you can still buy. You can always go the vintage route if you want a front panel machine. I should actually go into why a front panel machine. I worked for IBM for like 18 years, and when I started, every machine had a front panel because you could look at you know, memory, you could look at registers, you could look at basically anything. You could, for instance, I had a customer had a software problem. Specialist comes in, and he felt it was a software problem, but he could not write to a communications controller at the other end of the phone line. So the specialist comes in, he writes a hand loop using the front panel, executes it. He goes, what do you see on the screen? He says, zeros. He says, well, it works. You know, but this eliminated the operating system, eliminated hardware, software, eliminated everything except the hardware. Of course, you have to know the specific instructions for doing that, but this guy had a photographic memory, so I guess that helped, which I don't, but yeah, so that's the, that's one of the reasons for front panels though. But obviously with the advent of software monitors, like, I guess, I don't know which was the first one, but TDL down in Princeton, obviously for the S-100, they had their Apple monitor and then the Zappa monitor. The Kim-1 had a software monitor. The Southwest Tech had software monitors. And because of the advent of those, front panels kind of fell out of favor. But I think growing up in that era, I always wanted to shoot with a front panel just because I like messing around and talking to the hardware directly. Like I said, I'm not a great programmer, but, at least, I don't know, it just gives like more like a hands-on feeling. So that was one example using the parallel port. I had my serial port, but yes, I'm sorry, yes.
But your CPU card has to be set up for front panel, right?
It has to have, right. There are ones that can go kind of both ways, in that you can say, don't use a front panel or use a front panel. Most of the early CPU boards, like even the Kremenko ZPU, they came as replacements. So the thing is that replace here because The original M-size MPU board was only 2 megahertz, 8080. One quirk with the 8080 is it requires 3 voltages. It requires 5 volts, minus 5 volts, and 12 volts. So that's a lot of, you need extra regulators, you need, a lot of other stuff. That the Z80 was 5 volts. The Z80 was the little history was when one of the engineers, I guess Federico Fagin, I think his name was, he worked for Intel. He says, hey, let's do this. And they said no. He goes, well, I'm going to form my own company. So Zilog was born. So that's the thing. It has to be set up for front panel. I'll shut this off here for a second.
Yeah, I just thought you could just drop one in and boom, you got a front panel. But that has to cable over to
right, that's the thing. And without that cable, you can't enter stuff via the switches. It's interesting because this is it's 16-pin cable, but it's actually 8 bits across. Like across the dip header, they're connected. But if you put it in backwards and try and read from it, you're like, I try and read the address and the LEDs are reversed. And I've done it, so. But yeah, this is a Byte 8 CPU board, which was designed to be, obviously by today's standards, very Spartan board. But here's your front panel connector. Here's your 8080. Here's your regulators. There's a regulator. This is a nice one because it actually gives you voltage test points on top. But just similar. This is a little more complex than the inside board because the inside board, this is a priority interrupt control around. The inside board does not. The inside provided a separate card for that called the PIC 8. So, so you need,
So there has to be boards that have a socket for the inside panel. They were
exactly
as replacements for inside.
Exactly, yeah. So I had a nice demo plan, but since I don't have my adapter where I wrote to the serial port, I could actually it would come out on the screen. You can see it, and then read from type something in and have it come out in the lights. But unfortunately, I don't have my adapter, so I messed up a little. But that's what happens when you're rushing at 10 o'clock.
So the cable that connects to the front panel, I mean, is that made? I'm curious how you do the single step and various things like that. Basically, does it just shut off the clock signal that's being generated so the front panel controls that?
Yes. There's a circuit I've seen with flip-flops, and it works. I forgot exactly how it works, but basically what it does is it reads the processor ready signal, and then so it runs it for one instruction cycle, and then it turns it off. And so, but you bring up another interesting how the front panel works itself. It actually takes the address. It basically stops the processor. The processor's there. It runs it, and basically, but it jams. It actually puts the processor in kind of like another region, jams the address onto the bus. Actually forces the address onto the bus. It's a jump instruction. Okay. So, if you look through an inside front panel schematic, you can actually see where
the C3.
You can actually see right. You can actually see the C3, and then the other bytes are filled in from the switches. So it's interesting how they did it. A lot of people are like, well, they're breaking the rules. It worked for the Altair, it worked for the M-side, and it worked for like I said, the Byte 8 and the Ithaca DPS-1.
It's funny because that same technique, if you look at some of the early Spark CPUs, like when their like vector register is actually a jump and then the location to jump to. So it's essentially a jump table because it's easier to do that than to figure out how to do pull it out of memory and say, okay, I could go there. Just execute the instruction.
Yeah, use the jump the other day.
Yeah, so like I said, this board came out in probably, I don't know if it has a date on it. It's probably, my guess is probably 76, 4 of 76. So, and the Altair came out in 75, and the M-side was kind of right behind it. Story behind the M-side was, they wanted to buy one because they had a project they wanted to use it for. MITS said, we can't send you one. We're too swamped. So then the engineer said, well, we'll build our own. And it became as successful and more successful. One nice thing about this type of panel is it's easier on the fingers than those toggle switches. Because you're loading these. This is a dream to flip. Those little toggle switches, they actually start to hurt after a while. I don't have an Altair, but I have an Altair clone. Basically, it emulates the entire Altair on the PIC32 that's located on the front panel. Works exactly the same, except no disk drives. The disk drives are in flash storage. So, and those switches do get to you after a while. So that's, this is like way back when, but they're still developing cards for the S-100 bus. So, like for instance, this is from a fellow in Canada called Josh Benson. It's a single board computer.
You'll be here.
Yes, yep. Yeah. Single board computer, 2 communication ports, 64K of RAM, storage via SD card, parallel input and output ports. I think that's pretty much, it's pretty much the deal. And so what it does is the way this one works is when you bring it up, it takes the contents of the ROM and writes it into higher memory. Like, I think it's dog, baker, and above. And so now, because of that, you can actually run CPM on it. The CPM is on the card, so it knows that that's where the CPM file, like the BIOS and everything else is. So it's just amazing because he put all this functionality on one board. It'll work with either inside or Altair front panel. So the point I'm trying to make is that they're still developing new boards, for the S-100 bus.
What CPU is on that one? What CPU is on that one?
8080.
8080.
Yeah, he wanted to be accurate. It runs a little faster. I think it runs at like 2.48 or something, just because the divider because when you divide that down for the clock for the UART chips, it comes out to an even number. That's why I did it that way. Because running at 2, you got to do a few gyrations to run the UART. Because back in this day, the UARTs, the communications controller, were on a separate board. So, you didn't have to worry about that. The board had its own clocks. Here, he's running it off of trying to save space. So I'll just give you a little demo of this.
You said that has 64K of RAM. So how the 8080 can address how much total?
64K without bank switching.
So it has to do bank switching.
Yeah, what they did was there was a couple standards. The one I'm most familiar with was Kremenko. I think it was output port 40. You could write out to output port 40 and enable or disable boards that are in the system. So for instance, that's how they did it. So for instance, I have a little Kremenko setup with a Kremenko floppy controller, a CPU board, and a memory board. And the way that works is, first thing it does is it disables the upper 16K of memory. Okay, and then the floppy controller comes in, and then he basically loads the files up there. He loads the files up there, or I should say, the board is addressed there. So he reads, off the, reads from the floppy, and then he enables the memory. So now you're back your full 64K. So it's like an interim step. So it's a little easier with the monitor, the software monitor. This is a later, he did a couple of revisions of this board. This one, the cable plugs straight in. On the earlier board, the cable gets twisted. He has this connector upside down. And if you just plug it in, like I said, you wind up with, why is this all backwards? So.
Bust on for that.
Yeah. He's coming out with a new version of this because it is expensive to build since it has so many chips on it. Just pricing the chips would probably cost $300 or more if you source all the parts. So he's going to do a lot more. He's going to eliminate parallel boards and do a lot more of the stuff in software. Just because it'll be easier and it'll be easier to build, cheaper on the wallet. Because there's like thousands of connections on this thing. Because you got to buy this as a blank board. So yeah, he doesn't. He has offered some assembled through eBay, but but now he's all out. Because I asked him, because I was working a trade with him, saying, "Hey, you got any boards? I'll trade you." And he goes, "Actually, I'm all out." So So, any questions in the meantime? So sorry, I'm a little flustered because I forgot my adapters.
If I may mention,
Sure. Like a 9-pin, like either male to male.
Gender.
Yeah, gender changer. I'm sorry?
I want to mention, you mentioned copying ROM into RAM.
Right.
Long ago, there was another reason for that. The ROM chips were very slow, 450 nanoseconds and slower. RAM chips were a lot faster. So some systems would copy the ROM into RAM and then run at full speed because of that. Now, it sounds silly in a way because once it's in RAM, you can overwrite it, you can trash it. So now your ROM isn't really ROM. But it also meant that if you only needed it once, you could reuse the memory. So it was used at your own peril.
And you can patch bugs in it too on your own. Yeah. That's
Well,
what they say about
That
it.
never happened.
Hey, oh, no.
But anyway, that's one of the weird things that it was not explained to me on a system I was working on. So they said, well, we copy the ROM into RAM. But they wouldn't tell me why. It took me a while to understand. It was simply that it was a speed issue. So that's a whole other world of startup things. Sometimes the CPU will start up at one speed, then go to another. Kind of like when we used to have the switch for turbo mode. And now the Pentium has that too. It's called power management. They'll go at high speed when possible, then it overheats and it starts backing off the clock.
Yeah. So this is, like I said, this is basically a new product that Josh came out with. Like I said, he's doing an updated version. But so now when you power it on, so now it's presented. Do you want to go into the monitor or do you want to boot CPM? So now if you go into the monitor, so there's your menu. So these are the things you can do. For instance, if we want to write something to this output port, which is FF, we're going to write FF because it will turn all the LEDs off because of the inversion. So we say output, Fox, oops, output, Fox. It'll turn all the LEDs off. So this obviously is a lot simpler way of testing things. But, this is a new board, so, or newer board, so back in the day you really didn't have this. But it does make it handy for testing stuff that you get. One nice thing about this is you get your 64K memory space, but you can unjump or unselect 8K blocks. So what you do is, like, say for instance, if I wanted to test, I'll give you an example. So, for instance, say if we go into CPM. So now this is our typical CPM directory. Okay, so this is our CPM directory. Now, for me, one of the most powerful commands in CPM, it's not a command in CPM, it's a program, I should say. Let me rephrase that. Survey. It'll give you a survey of the system. It shows where your RAM is located. Say this is where CPM is located. So it'll tell you that your CPM is located there, your BIOS is located there, and it gives you a map of the memory, shows all the ports that are active in the machine. For instance, I have this address as Fox Charlie. There it is, FF. The serial port is the address to the 0102. It's up there. So, for instance, if we go back to our logic probe, I'll do that.
So, a question on the I/O port. So,
yeah.
And I don't know anything about S-100, but that's one of the reasons I'm here. Is that is it actually a registered bus in the sense that there's a way to enumerate it? Like, does it actually no, because when you put the card in, the card says basically
what this
or
board
does
is
it
doing,
probe it and
that's
just
what this is
figure
doing, right? So if you have two cards with the same address, you might have a conflict.
Okay.
You know, that's the thing, because it doesn't know better. It's not like you said, there's no registry that says, okay, there's a card at this address, this is what it is. It just knows that there's something at this address.
Okay.
You know, like, for instance, I could address the serial port to be at Fox Charlie.
Gotcha.
You know, and you know, if I went to access it, it might hang, because now they're both trying to drive, when it comes back, they're both trying to drive the bus at the same time. So, so that, you know, that can be a problem.
So there's no notion of a command status bar to set up a serial port or anything like that. It's all hardware on the board, every single thing, and you just talk to the IP address.
Right. Like this board has a, you know, this has status of, these are hardware UARTs, which are relatively easy to interface to software-wise, because all the interfacing, it's all done through the hardware. You set the baud rate, you set the, you know, how long the word length is and stuff like that, all through hardware by jumpers, or in this case, switches. So that makes it easy. Where the software UARTs depends on software. You have to initialize the UART. You have to send it the proper command so it knows what divisor to use for the baud rate. So I kind of like these because it's either going to work or it's not going to work. It's not kind of like, oh, I set that bit wrong.
I was amazed when you did that, just how easy that is to get back and do that, because there's nothing to set up.
Right.
It's just there.
Right. That's why I like doing it, like I said. But you know, and I have zero programming skills. I mean, I took programming in school. I've done programs. You know, to sit down and write code like a lot of people. You know, it's like kind of like I got to write everything out on a piece of paper and say, okay, what's this instruction do? Like I said, I'm not really a software guy, but I enjoy building stuff. Like I said, I had an Insight back in the day, so you know that's kind of a, you know, it's kind of like a lost love. I sold it to buy an Apple II back in like 1980.
Good move.
And I love the Apple, but as soon as I could afford it, I wanted to buy an Insight again. So I actually have one at home, and I have an integrated systems too. So now to, for instance, we'll go into memory. We'll just test a small piece of memory, just to give you an idea. So, for instance, if you go into the monitor, you can do a RAM test. And so we're just going to test, you can't test low memory and you can't test high memory because that's what the monitor is. So if you try and do it, it'll just hang because you're overriding the monitor, if you will. So we'll do something in the middle. Say RAM 80 for to 8 Fox. So that's now that's a 4 gig lock. So it goes through and it tests memory, and you know I'll probably stop it early and go through the whole thing. But so that you can use this to test memory too. But like I said, one of the nice things about this board is the fact that you can, you know, you can remove memory, so that now you can plug in boards and test them.
Are there like a known set of CPM utilities for doing like testing and probing and stuff like that?
The survey for the probing, yeah, the survey is the only one I found. I'm not a CPM expert, but survey, it's a good because at least it tells you what's in the machine and what can identify. Okay. For instance, when I was messing around with this yesterday, these switches, I bought this board. I don't think this board was ever used. It was still in the original packaging. The switches have been sitting there for 40 years. So now I go to address it, I can't find the board. Because the switches, they're not closing because they're, after working them about 50, 60 times, then it worked. You know, so that was because like here, I had this thing addressed as, like I said, Fox Charlie. It can tell me, well, it's Fox 8. So I was like, okay, let's switch. You know, so then it works. So, yes, so this gives you an idea. You know, but like I said, when you're dealing with 40-year-old hardware, you know, I tend to, especially with the S-100 systems, I'm okay technically. I'm not a wizard. I worked for IBM as a customer engineer, but everything there was based on diagnostics. I mean, we never got down to the board level. You know, if you got a good understanding of diagnostics, you knew what to replace, and you replaced the whole board. we never got down to components. So consequently, I'm really kind of rusty on, troubleshooting with a scope, although I have fixed quite a few things with a logic probe. Which will actually, let's just stop. That'll just give me an idea. We'll go back to that. So I'm going to reset it. I'm going to run the monitor. So now, I'm sorry, go ahead.
Sorry.
No, yeah, sure.
When the front panel's plugged in and you're running the monitor like this, does that actually slow down the performance of the system?
Yeah, no, not at all.
So it's not stalling the CPU to just do the display aspects of the front panel.
Right. What's interesting is, notice when I hit reset, now it's going to the ROM initially. First instruction is a jump. See? Now the memory is on the same board, so internally he's already moved it, and so that first instruction is a jump. So now if you run, or you can actually look at the next one, examine next. So it's jumping to 0 able. Okay, so that must be where it moves the memory. Yeah, so here's where it goes. I remember I said, so here's it outputting. So I think that was enabling, but so you can actually see, you can actually see, what, it's another output instruction. You can actually follow through what he's doing, in his code. So what I do is if I want to test something, a hardware piece without using his setup, you can either disable the ROM, or what I do is typically I just go into the middle of memory somewhere. It's not effective. For instance, he's going to 8,000. Okay, so now we're in the middle of memory and he doesn't care. I stopped it. So now here I can actually input my program. Say this program here. All right, so what we're going to do here is, so now we're going to read my switches. I didn't have to. Let's look at that. Examine. What's the wrong thing? Oh, no. Okay. 8,000. So now, we'll have that in a second. So now, let me go back to it. Our input instruction. So there's our input instruction. On to the next. And I'm going to output it to that port. So it's going free. And now that port is Fox Charlie. So we do our jump back to the beginning. So now we're going to 8,000. So we deposit zeros. And we deposit that. So if I did this right, we're going to examine 8,000 just to make sure I did it right. Can't talk and do it at the same time because I'm challenged. Okay, so now we're going to examine the next. So we're reading from the ports, we're writing out the Fox Charlie, and then we're doing a jump back to 0080. So now if I say reset it, examine memory, examine. So now if I say run, 8,000. Right. And I'm at 8,000. So now, like I said, this is attached to the high order bit. See? I mean, it's just two different ways to test stuff, but, it's basically, like I said, the serial demo was a little bit better, but since that ain't going to happen, unfortunately. But, so that's basically, just some simple troubleshooting you do. You can check memory. You know, you can check memory. You can work on your input-output ports. Even some things like some of the floppy controllers. They're very complex devices, but typically, they're almost all of them are port-driven. You can output a seek instruction to the floppy drive, and if the floppy drive seeks, you know that you have it seek to a track. If you know if it seeks, you know that hey, it's not it's not DOA. It may have other problems, but it's still a quick test to when you're reading through, because most of these boards are 40 years old. The thing is, the chance of getting a brand new board that works as it did 40 years ago. One of the worst offenders is back in the day, like when I built my inside, they had these TI low-profile sockets. Everyone saw they're great. They're terrible. 40 years, they get oxidized. They grip the pin sideways, kind of. So eventually, those things weaken. They don't make contact. They fall off, and they become nightmares because you reseat the chips in the board, it works, and the next time you go to use it, it doesn't work. It's just because they're not really good sockets. But at the time, people considered them good. So like I said, that's what I built my machine with. I tend to use what they call double wipe sockets, which the socket is like this, and so now when the pin goes in, it goes in between the two pins, so you're actually getting contact on both sides. I'm sure they're not perfect, but the thing is, you're doubling your chances. A lot of the sockets only have a contact on the inside, so now you're doing that. Now it can become oxidized. It may not work because, like I said, on these, you wind up with a lot of problems due to oxidized sockets. The best are, like I have here for the front panel, the machine pin sockets. Where they're actually turned. They're actually turned on a machine, and they're basically circular, and they basically grip the leg from all sides. But they're probably 5 times as expensive per socket than a double wipe socket. So that's the thing. When you're adding, say if you're building a board like this board, it may be great, but you're probably adding over $100 to the cost of building it. So that's the thing. So that's kind of it. And it was just like an introductory, like I said, it was an introduction to front panel machines, just showing you what's available nowadays. These pop up on eBay. The blank boards are on eBay, like pretty much all the time. And the interesting thing, too, is because of people are getting more and more involved in the retro computing scene, the MSI, the original MSI MPU-A board, some fellow just made reproductions. So, so you can build those, like I said, those. Don also was working on a full-size MSI front panel, but I don't know why that project kind of stalled. But this basically has all the functionality in about 2/3 the size. It was based on the original schematics. They reworked a few things because of the way they used like an asynchronous counter, and it wasn't as reliable, so they changed some stuff to synchronous counter. Josh, the same fellow that designed this, helped Don out on this one. Really sharp guy, yes.
Besides the boards, how is the availability of the chips?
Not so bad yet. 8080s are still pretty commonly available. Most of the chips on here are TTL logic. These are like the 8212 input-output ports. These are actually like driving these LEDs too. It's a latch or input-output port. Depending on how you wire it, it just uses an 8-bit latch. They are they're no longer manufactured, but there is also second sources. There's also second sources like NEC made them, AMD, I believe. And then also there was, Signetics. There's also a 7400 series equivalent called the 412. 74S412, which if you can't find an 8212, the 412 is an equivalent. The UARTs, they're old, but they're still pretty commonly available. I'll be the first to admit I'm a scrounger. So like whenever I'm a ham radio operator, whenever I go to a ham fest, which is basically an electronic flea market, I look for piles of boards. Because there's sometimes you want a crate full of boards for $5, and I pull the chips off. Some of them are socketed. I have a desoldering tool. I remove them. But that's how I, for the hobby stuff, that's how of course, you don't want to see my garage because I got boxes up to the ceiling because I'm a pack rat. But luckily, my wife, she's tolerant. So, but the thing is, yeah, I have a lot of chips, But just because I know you can still get everything on here, but in 10 years, probably not. Who knows?
So we're at the point where availability may become an issue.
I would think so. Yeah, except for the new designs. This guy named John Monahan. He's in California. He's done a whole bunch of new designs. Brand new Z80 boards using all pretty much commonly available parts as we speak. Again, five years down the road, something gets discontinued, you don't know. But there are new designs that use modern chips. But for the most part, all through-hole soldering. Because I don't do surface mount. I've done very little surface mount. And I don't do the reflow thing. I actually use a soldering iron, so it's difficult to do surface mount stuff with a soldering iron, at least for me. As I'm getting older, my eyes aren't that good anymore. So, but some people can do it. I can't. But so basically, yeah, all the chips are still available, but like here, he's using 8250s, which came out a little later than these hardware UARTs, but these were available. A lot of early PC boards used them, for the IBM PC, or they're the follow-on products, which were 16 450s and 16 550s. Those are communication ports that were backward compatible, but they had bigger buffers, bigger FIFO buffers and stuff. So basically, yeah, you can still get the parts, but but that's why, I'll be honest, if I have one of a board, I always have two of a board, just because I can, it also helps to troubleshoot. Because, especially when you get in the area of programmable logic.
1 minute.
1 minute.
1 minute. Yeah.
Okay, yeah. Especially when you get in the area of programmable logic, like GALs, PALs. These guys like CompuPro used a lot of them. And now, unless they publish the equations for them, you're out of luck. Unless somebody reverse engineered them. So that's the thing. I try and stay away from boards like that, although they are reliable. But if they ever go bad, So anyway, thank you. It's like I said, I went through a little bit of a different demo, but unfortunately, I must have missed something. So, but you kind of got the gist of it. You can do a lot right from the panel.
Thank you, Jeff.
Oh, you're welcome.